Welcome! In this video, we'd like to introduce you to some research topics of the Fraunhofer Group Comprehensible Artificial Intelligence by way of a demonstrator. Our goal is to make AI systems trustworthy and comprehensible using explainability. Hence, we will present explanatory methods which help to make the output of such systems understandable to humans. Furthermore, we will discuss interaction possibilities that allow human experts to refine machine learning models and correct errors if necessary. AI techniques become more popular each day. Deep neural networks are particularly often used as they allow to extract and classify relevant features easily. We will focus on the use of such neural networks for image-based diagnostics and industrial quality control here. The success of deep neural networks is based primarily on their ability to automatically learn complex features and patterns from large amounts of data that are difficult or even impossible for humans to implement manually. However, a major challenge with such deep learning and other black box models is their lack of transparency and explanations, which makes it difficult to validate their trustworthiness. When it comes to quality assurance, though, it is important that such AI systems reliably detect defects. In addition, stakeholders such as engineers and customers want to be able to understand why the machine learning model makes a particular decision. To do so, the underlying decision parameters of the black box have to be made transparent. This way, human experts can detect a false decision and, in the second step, revise the decisions or rules made by the model, thereby following an interactive human-in-the-loop approach. This is where our demonstrator comes in. We try to develop explanatory methods for the experts to enable them to understand how the underlying neural network works. The methods our demonstrator provides are based on human explanatory approaches. Suppose Anna asks Ben whether the insect in front of them is a bee or a wasp. Ben points to the distinctive black and yellow stripes and its body shape and says, "It is a wasp because the stripes are so prominent and the typical wasp waist can be seen." Generally speaking, Ben highlights the crucial areas and describes them verbally. This is the idea behind the verbal explanation of our demonstrator. In other situations, we classify an object by comparing it to singular or typical images of the object class. While picking mushrooms, Anna clearly names a mushroom as a button mushroom, but Ben is unsure whether it might be a tuberous leaf mushroom. Therefore, Anna shows him pictures from an identification guide of both button mushrooms and tuberous leaf mushrooms that look very similar to the mushroom in front of them, as well as prototypical pictures of a button mushroom. Based on these pictures, Anna deducts that the mushroom in question is more similar to a button mushroom. The demonstrator's second explanatory method uses this approach. If Ben is still not convinced by Anna's explanation, Anna can also verbally point out the typical characteristics of a button mushroom, which brings us back to the first approach, the verbal explanation. Just like us humans, the demonstrator can combine explanatory approaches to ensure better understanding. Again, the demonstrator provides two explanatory options. Choosing explanation by example depicts pictures similar to the input image so that their characteristics can be compared. Cognitive science research shows that explanations by example are highly effective for humans to grasp complex concepts. Secondly, the verbal explanation highlights those features of the image that played an important role in its classification. We have trained the AI model using two datasets. The MNIST dataset is used mainly for academic and research purposes to distinguish the numbers 1 and 7, whereas the quality dataset is a more industry-centered approach where disks are either classified as defect or as OK. Hence, our explainable AI approach predicts the category of an input picture across different domains and can therefore be applied in different contexts and application fields. To select an image, one chooses the preferred dataset and clicks on it. 4 times 4 images are depicted randomly from the whole set of pictures, and an image is selected by clicking on it. The selected picture is classified automatically based on the previously trained CNN. Now the image actual class, the true class, and the prediction of the CNN model, the predicted class, are depicted. If the predicted class is correct, so it is the same as the true class, it is highlighted in green, otherwise in red. Next, the classification of the image is explained by depicting the nearest hits or misses, as well as prototypes of the assigned category, or by giving a verbal explanation of the characteristics of the chosen data point. Let us explain this further, considering one dataset at a time. First, let us look at the well-known MNIST dataset to understand the concept of the demonstrator with the help of a simple example. The AI system is supposed to determine whether the selected image is a 1 or a 7, both in American notation. Afterwards, we will show the actual industrial application of the demonstrator using the second dataset. We have chosen a 7, which has been correctly identified as a 7. But how did the algorithm identify the picture to be the number 7? In order to answer this question, the first explanatory approach, explanation by example, depicts similar pictures that have also been classified as a 7, the near hits, or as a 1, the near misses. Additionally, the AI system chooses 3 prototypical pictures of a 7 that are depicted. These examples should help to identify the most crucial features or characteristics of an image for the algorithm to detect the number 7. For the verbal explanation, the second explanatory option, 3 images are depicted. The original unaltered picture, the image mask comprising detected lines, as well as picture and mask combined. A written or verbal explanation is provided. For example, the image is classified as a 7 because it has a horizontal line at the top, which is characteristic of a 7 but not of a 1. On a technical level, the algorithm learned logical rules to distinguish 1 and 7 by using inductive logic programming. A 7 typically has both a horizontal and a vertical line, whereas a prototypical 1 only has one vertical line. After we have given you an introduction on how the demonstrator works, we will now show you the practical relevance of these explanatory approaches. The quality dataset contains images of real brake discs from an automotive manufacturer, as they are used in industrial practice for quality control. These are classified as either defective or okay. The demonstrator again offers 2 different explanations, explanation by example and verbal explanation, via drop-down menu. As explained before, we have used the CNN on a dataset to classify its instances, but also to use feature extraction on that model to obtain embeddings or vector representations for our images. These embeddings are sensitive to those aspects of an image that relate to its inferred class, and therefore map images with similar class-relevant features near each other, which is the basis of our near hits and misses explanation we will now explain. This approach is called model-specific, for our embeddings are extracted from the previously defined CNN model. Using this model-specific approach, near hits, near misses, and prototypes are presented based on a distance measure. All instances of the datasets are represented as vectors in a multidimensional space, the embeddings, and those instances, or vectors representing instances, closest to them in the multidimensional space are depicted. Near hits are those closest with the same classification and are thereby the most similar elements from the training data, whereas near misses are the most similar ones of the opposing classification. The number below each picture states their similarity within the distance space as calculated by a distance metric. The closer this number is to 0, the more similar the pictures are. Thereby, near hits and misses define the local decision boundary of the prediction at hand. Prototypes are the most typical instances of that class and used to globally explain relevant characteristics of an entire class. They are selected via maximum mean discrepancy, MMD, so via a similarity measure. As research shows that the curves flatten considerably around m equals 3, 3 prototypes seem to be ideal, so there are 3 prototypes depicted here. Additionally, one can choose options, namely the number of near hits and misses that should be depicted on screen and the distance measure to use. As stated before, each element of the data subset is compared to a data sample, either with the same inferred label, near hit, or a different label, near miss, by a metric, either a Euclidean metric or a cosine metric. Obviously, choosing a different distance measure may lead to different near hits or misses. Secondly, the verbal explanation translates the output of a saliency map into human-readable prolog rules. As inductive logic programming requires horn clauses, the image mask is firstly partitioned into superpixels using attention-based explanation. Hence, those image parts, or information, responsible for classifying the object, e.g. as defect in this case, are highlighted. Various components or properties of the image and its superpixels, e.g. has size, are then computed. These computed properties put together make up the horn clause, as they consist of a list of true or false axioms. They are put into prolog rules and are thereby a concrete explanation. For example, if there is a large indent close to the center, the disk is damaged. Each return clause, each combination of attributes leading to defect, is considered a sufficient condition for classifying that image as part of the target class, defective, and each of these clauses or rules that apply to the given data point are then depicted here as the verbal explanation. In this case, it is that the total volume is medium. In this video, we presented the demonstrator of our explainable AI approach. We use a combined approach with the CNN for classification and similarity measures or prolog rules to explain the previous classifications. As mentioned earlier, the idea of this two-step approach is to make the decision parameters of the underlying CNN comprehensible for human experts by means of near hits, near misses, and prototypes, or by providing a verbal explanation. As the demonstrator enables human experts to grasp a machine's decision, the next step of our research group is to incorporate feedback or corrections to meet the second step of the human-in-the-loop approach. A person who has understood the decisions of the system should also be able to correct these decisions. For this purpose, we plan to implement methods for the adaptation, correction, and refinement of machine learning models. If, for example, human experts are dissatisfied with the classification, or if the given explanation is not correct, right for the wrong reasons, a way to ensure the classifications make sense in the end will be provided. In addition, we hope to be able to extend the application to other datasets and use cases. If you have any further questions, feel free to contact us. You can find the contact details on our website. We look forward to hearing from you.